Before we get started on our second video, we need to make a change. I had the diode placed incorrectly. It is actually on the coil side of the capacitor resistor, not on the ground side where I had it. It is just a protection diode. We can take that out and it makes no difference. It's only there in case the LED blows, and our current will then be sent in a loop rather than back to my signal generator. I'm getting in the habit of protecting things. Alright, so there's been some questions about the transformer, and I've taken one out. Now, for those that didn't see it on the first video, this is what the transformer is. There is the brand AC converter, step down converter. So it's a transformer or a converter, whatever you like to call it. And there are the details. This is what is inside, and this is what we are using. Both coils share a common ground and are wound on the same former. There is no gap like in other transformers where you'll have the primary here and the secondary here, or vice versa, and then the E-core around it. It is not like that. This section in the middle is not there. They're both wound on together. So that's exactly what the transformer is. The other ones that I have taken apart, taken the cords apart and tried to unwind the wire to save it, because it's not actually glued on, but they are wound on together and become a very tangled mess if you try and save the wire. It's like they've done two wraps with one and then one wrap with the other to get the 2-to-1 transformer. So both windings are wound on together. It's not one winding and then another one on top. They're both wound on together. So hope that clears that up. Alright, so same circuit as the first video. All we're doing now is scoping everything. And it is that bit I'm very interested in, now that we know for certain that both wires or both coils are wound on together. So all the wires of each coil, the primary and the secondary, are all mixed in together, intertwined. And that begs the question as to how one manages to ring and the other one does not. When the inductive coupling, you should get them both to ring exactly the same, but they do not. Alright, so running through this, we've switched up to 5 kilohertz, 3 volts peak to peak, with a 1.5 volt offset to give us a 3 volt pulse. 0 volts, a 3 volt pulse. Impedance is at 0. We've gotten rid of that because that dropped the voltage down to 1.5 volts on my signal generator if I switch to a 50 ohm impedance. Probably don't need it because we have a 100 ohm resistor here in line anyway. Alright, so we know the circuit at the moment. The scope is hooked up over the primary and the secondary and our common ground. So our blue trace is hooked up to the secondary, so the ground will be here, and I have it before the LED, so the probe will be here. The yellow trace, ground here, and probe here. So that's what we're looking at on the scope. Okay, this meter, as before, is reading the voltage across the cap and resistor combo. So our voltmeter is placed here and here, and I have the negative of the voltmeter here and the positive here, and at the moment you can see it is reading correct, 24.7 millivolts. according to our current flow. Our amp meter is simply in series with the positive of our signal generator. Goes through the amp meter, out of the amp meter, and back into the primary coil of our transformer. 240 microamps at the moment. 24.6, 24.7 millivolts, or we'll say 24 millivolts over 100 ohms is 240 microamps. Okay, so we know what our 2 meters are reading, and we can see that our secondary has a nice ring and our primary has a little bump at the start and then bugger all. You will also notice the voltage on the secondary never goes back up to 0 volts. It always has a negative voltage. I'm set on 1 volts per division, both channels, so we have about 0.4 volts or a negative 0.4 volts, minus 0.4 volts, however you want to say it. That's what we have. The primary voltage is probably about minus 0.2 during the rest phase, and this is because of this cap. If I take this cap off, the primary voltage will go to the 0 volt line, but the secondary voltage will stay exactly where it is. Alright, so what we're going to do now, we're simply going to reduce the duty cycle. Now, because I've raised the frequency, I've also had to raise the duty cycle to get this as it is now with our LED going brightly. This will work from 40 Hertz up to 15 kilohertz, and when we do a current trace, we can actually get the waveform to be heading up, give it a kick with the primary to be in complete resonance, and this happens at higher frequencies up around 15 kilohertz, but for this video we're just going to look at the effect of what our 2 meters are showing here. And we can confirm this meter by the voltage across our 100 ohm resistor. The capacitor is simply there to smooth things up a bit, otherwise it gets a bit noisy, but we can indeed remove the capacitor and we will have exactly the same effect. So our 100 ohm resistor really is being used as our current sensing resistor. It is just on the negative side instead of the positive due to the common grounds of my equipment. Alright, so time to wind it down to 5% duty cycle. I'll give you a look at that again. 240 microamps and 23.924 millivolts across our 100 ohm resistor. So one confirms the other. Okay, down to 5% we go. And this is the effect that I wanted you to see. So now we have a negative current of 520 microamps. Now what this meter is doing, it is averaging out the current per cycle. So we're not seeing a 520 microamp pulse at our 3 volts. We're seeing 520 microamps per cycle. So that's the way these meters are designed to work. They average out the current. So each individual pulse, of course, would be a lot higher. So what this meter is telling us at the moment is that there is more current flowing out of the device than what is flowing into it. So once again, if I turn this up to 10, we now see we have more current flowing into the device than we have flowing out, because the meter is averaging the current flow. excuse me, per cycle. Now at 8% duty cycle we start to get a reversal in our current flow, and we now have 7.6 millivolts across 100 ohms, which of course is our 70 microamps. So we'll go back down to 5%. So now we have 520 microamps of current flowing out of the device. So the meter is telling us there's more coming out than what's going in, and if we look at our voltage across our 100 ohm resistor, we know that voltage across our 100 ohm resistor indeed gives us that current. Now this meter is reading a smooth voltage. There's very little ripple across that, which we'll have a look at in a minute. So, but it is the ringing of the secondary and not the primary that is really interesting, because as we've seen, both the primary and secondary are all wound on the same core and intertwined. So I'm really not sure as to why we get that. There doesn't seem to be any inductive coupling, or very little, between the primary and secondary during the ringing phase. When the pulse switch is on, you can see both the voltage on the primary and the secondary go up together. There is no phase difference between the two, but you will see that the primary switches off, overshoots a little, then comes back up to the 0 volt line, whilst the secondary maintains its voltage a lot longer, and it is actually the secondary that's running the LED, not the primary. So I also find that very interesting. So we'll drop it down to, say, 3%. So now we have a negative current of 840 microamps and 83.5 volts across a 100 ohm resistor. So the two are still reading much the same. What we're going to do now is I'll take the red trace off, and I'm going to place that across our resistor. Actually, yeah, I will try the red trace. Unfortunately the clip on the red trace is a bit dodgy. So what we have to do, my trigger is set on the on channel A, yellow channel, and that is why we are not doing so well at the moment, because we have nothing to trigger off just yet. Now, herein lies the problem, which I might switch over and trigger off the blue channel. Where are you? There we go, that's better. Alright, so I'll lift that up to 50 millivolts. So our yellow trace is now across our 100 ohm resistor, and that's showing, where are we, channel 1, voltage minimum, voltage maximum. I haven't got that in there. What we want is a mean voltage. Channel 1 mean is 84 millivolts and we have 83.7, 83.8. So our meter here is very accurate at reading across our 100 ohm resistor. But you will see I do have the scope probes around correctly, and you will see that the invert is off, and I'm also using a DC coupling on both channels. So if I wind that back up to a 10% duty cycle, you now see we have a forward current across our 100 ohm resistor, so now things are flowing in the right direction as both our meters show us. If we drop it back down to the 5% duty cycle, you will see now the current is flowing in the opposite direction, even though we haven't changed anything on the signal generator. So our mean voltage now is a negative 54, and we are showing 53 millivolts and 530 microamps. So all normal, other than the fact that it's now flowing out of the unit instead of into it, the bulk of the current. We obviously still have the pulses going into the unit, otherwise the LED wouldn't be running. That's the interesting effect I wanted to show. If the camera work's been a bit shaky, making you a bit seasick, sorry about that. This just would have been too hard to flick across the device and our meters and the scope and the signal generator on a tripod, so you'll just have to put up with it. So that's what we have. It would seem that there is more current coming out of the device than is what's going into it, and this seems to be confirmed by both the meters and the scope. At this point in time, I must believe that it's something to do with the signal generator, because something this simple couldn't possibly be anything too wonderful. It was basically to show you what I'm seeing on this very simple setup, which once again is that. So what I'm going to do next, I'm going to swap the transformer out, try it on one of these and see how I go. Now, because channel 2 is ringing and we have a reverse voltage through that ringing, I should be able to put an LED the opposite way and get that to go as well, but I may have to put a switch in there so I can switch it on once it fires up. So I'm not really sure how we'll go sending current back the wrong direction via the LED. I'll have to have a look at that. So yeah, that's what we have. Everything is arse about when we get to a certain duty cycle. So the other thing we were going to have a look at while we're here is I'll have to turn that back down. Now if I turn the voltage down per division on the A channel, you can see, I'll just switch, no I can't switch B off because that's what we're triggering from, but you can see a slight ring there, very slight. However, I thought it would have been much more with that transformer wound the way it is. It should be the same as our blue one or our secondary, maybe half the voltage because it's 2 to 1, but nonetheless it should have been much better than that. So what we were going to try and do here, oh that's the wrong one, I want to shift that across. a wee bit, probably not that far. Alright, so I'm going to trigger back off channel 1 now, as it seems to be a little more stable. Okay, so what we wanted to do is raise the frequency, going up to 15. See if we get that there. Yes. Okay. So what we want to do, I might even lift that up to 20 kilohertz, just so it becomes a little more apparent. So you'll see now on the ring our voltage is on the way down, and we've hit it when it's on the bottom. What we want to do is hit it when the wave is going up with the pulse from our signal generator on the primary. So it just gives the voltage is already heading in the right direction, and we want to get a bit of a kick with our signal generator, and we simply do this by adjusting the frequency. Until such time as we get it as close as we can. And you'll see there it started to drop back down. We want to get it right on the pin or the crest. Oh, I went the wrong way with that, didn't I? Okay, so that's pretty close. So you can see that our voltage on our secondary was on the way up, and just as it starts to turn, or the voltage starts to level out, we've given the signal generators sent in its pulse of current and given it a kick. And you can actually see the effect in the brightness of the LED. If I go either side of that, the frequency, oh, we've just jumped straight over to the next one. And you can see right there that it dulls off. So that's bright there, bright there. If I put it in the middle in the dull spot, you can see the voltage was on the way down, and then we kicked it. If we turn it back so the LED is bright again, like yay, you can see the voltage on the secondary was on the way back up, and then we've kicked it. So we're in resonance with the ringing of the transformer secondary at the moment. That's at 38 kilohertz, probably a little high. We'll go to the next one. And looking at the LED, oh, we've gone way over. And the ring's petered out there at 5 kilohertz, but anyway, that's what I wanted to show you, is if we bump the voltage back up, we also have that set on 500 millivolts per division. So that's one of the most interesting things to me, is the ringing on the secondary, but as you can see, diddly squat on the primary. And like I've said before and shown, both windings are wound on together. There is no gap in the middle. It may be a little more explainable, but not really, because it's got a steel core through the guts of it. But with the two windings separate, we may get a little bit of ringing on one and none on the other, but we have both wires wound on together, and we have an extreme ringing on the secondary coil and nothing on the primary. I'd like to see someone replicate that effect with a similar transformer, or even one like this. So that's about it. That's what we have. Apparently our meters and scope are telling us that the current is now flowing in the wrong direction, or the bulk of the current is flowing out of the system rather than the direction that our signal generator is pushing it into the system. So like I said, I think, well, I can only believe that it's something to do with the way the signal generator is set up inside, but I'm not sure why, because our pulses are 3 volts and then that is 0, as you've seen with our offset of 1.5 volts. So we had a 3 volts peak to peak, we've offset it 1.5 volts in the positive direction, so we have a 3 volt pulse and then 0 volts during the rest phase, or the off time. Anyway, I'm going to try a different transformer. I may even grab a microwave oven transformer and give that a whirl, see what happens. But at the moment we are using one where both the primary and secondary are wound together and they share a common neutral, as we call it here, or as in this system here we're using it as the ground. Alright guys, thanks for watching, and I'll see you next video with a bigger transformer. See how we go. Cheers.